Let us continue cloud computing module 1, second chapter. So this is chapter 1.2. You can see we completed this first part, scalable computing over the internet. And as I said, chapter 2 has 5 sections, which is 1.2.1, 2.2 like that till 1.2.5. So 1.2.5 is very small, like you just have two parts in it. And you don't have much about that last part. But oh, this is 1.1.2. Wow, great. So we are now in technologies for network-based system. So multi-core and multi-threading technology. Just a minute. So here we have three topics under this first one. 1.2.1 is there, right? So I'm just referring my handwritten notes and trying to make the part. So if I have to draw it, so this has a 5, right? 1, 2, 3. So 1.2 itself has 1.2.1 like that 5, and this first thing has 3. Okay, 1, 2, 3. Then 1.2 has again 3 same. I'll write this time, and 1.2.3 has 4, and 4 has 3, and this has 2. So if you see, if you divide this thing into each section, you will feel like, hey, it's just three topics. Once you complete each individual thing, and then if you combine, you will be like, oh, I have completed the whole step like that. So it was just a small breakdown of this section. We'll start with the actual explanation. The key points for 1.2.1 over here, you can see. It speaks about multi-core CPU and many-core GPUs, how they are used in HPC and HTC. They talk about instruction level parallelism and thread level one. About multi-core CPUs, they have three types of cores, that is L1, L2, and L3, which has a diagram as well. And since it has a simple diagram and very explainable diagram, so there are high chances that this question might be asked. We'll see that also in detail. Multi-threading technologies, it's like I repeat, you can repeat few same points like you have studied in the previous time, but you have to mention few specific points here as well related to CPU and GPU itself. Then about GPU, we'll speak about data level mainly because of DLP itself. We have moved towards GPU, like enhancement and growth in GPUs. The first part, advances in CPU processors. Let me just go to the beginning of 1.2. We'll compare both the notes which I have prepared and also the textbook notes. If you see the textbook part 1.2.1, as soon as it starts, we have a small, what to say, a graph over here. Advances in CPU processing. If you see, it's not much. It's just like hardly 2 paragraphs. So what will they ask in those 2 paragraphs? Hardly you can filter it to 4 to 8 points. That's what I have done over here. So here CPU and advances in CPU processor. What has advanced? First, the CPU speed has grown. From how much to how much? So it has grown, see, from 1 MIPS to 1,59,000 MIPS. So here, this was WAX 780 in 1978. And by 2011, Intel Core i7, which you basically see in your laptops whenever you buy it, they in that you have used Intel Core i7, so which is has 159,000 MIPS. So the speed you can see from 1 to 8, so you can directly say it's 159,000 percentage more than the first one. Like from 1978 to 2011, it differs from these many thousand number of percentage itself. The clock speed as well. See, speed from 1 MIPS to 159, clock speed from 10 megahertz to 4 gigahertz. See, megahertz and gigahertz, there is a lot of difference. 1000 megahertz is like a gigahertz, like it's like that. But power and heat limitations halted further increase. Then CPU use instruction level parallelism via techniques like CT techniques are there, superscalar architecture, dynamic branch prediction, and speculative execution. So this is a diagram for multi-core processor architecture. So you have multi-core. Each core has its own L1 core, okay, L1 cache. Then all of these L1 cache are interconnected not interconnected. They are linked with L2 cache. Okay, and this L2 cache communicates with L3 cache, which is DRAM, dynamic RAM. Okay, you can see here L1 cache is per core. Each core has one. Then shared L2 is shared for all the core. Then L3 cache are optional, off chip or on the chip one. So if you see here in the diagram, see, yeah, it wasn't that much. If you see advanced CPU, we done about multi-core pro CPU now and mini-core GPU. We have to talk about that. We'll move on. Multi-core processor is done and many-core GPU. So see, this both were combined in ours, right? So we'll talk about many-core GPU as well. CPUs are limited in DAB. Like I said, data level parallelism. That's why it led to many-core GPU development. GPUs have hundreds and thousands of thin cores optimized for SIMD style processing. What is SIMD? It is simple instruction multiple data. It is used extensively in HPC clusters and supercomputers. You know what is HPC clusters? The several MPPs, are converted to clusters. Clusters are, like tightly coupled. Whenever you remember about clusters, it's like suppose you have a ball, like a big one, like football, and inside that football, you just remove that balloon and you're filling that golf ball. So, suppose a big football ball, you just remove everything and you keep filling with golf ball. So all those golf balls are tightly coupled. So now this football is a cluster of golf balls. It's like that. Then multi-threading technology. You have to talk about how threads are processed. That's it. How threads are being processed or executed. That's the only thing you have to talk about multi-threading technology. With the name as it says, multi-threading technology means like more than one thread is processed or executed. It's there are one or two extra points. The first thing is superscalar processor. It executes instruction from one thread using multiple data paths. Like one thread is being executed with the help of along multiple data paths. Then you have fine grain and coarse grain. Fine grain, so see, very easy to remember. Fine grain switches thread every cycle. So pipeline, like you have instruction one clock cycle and all. So at every cycle, the threads are switched. But in coarse grain, the threads are switched only after many cycles. Many cycles, it's like a random type of thing based on the processor or the technology which they are using. It defines the number of multiple cycles, whatever it is, or it can be manually set as well. Then simultaneous multi-threading, SMT. You remember SMT? MT is nothing but multi-threading. S is just simultaneous. Multiple threads executed in parallel in the same cycle. So one clock cycle, in pipelining only one instruction is fetched. If you check, suppose three instructions are fetched. If you see in the third clock cycle, I1 is being executed, I2 is being decoded, and I3 is being fetched. So in the same cycle, you can see three different instruction and three different operations. That's what it is talking about. Dual core CMP. What is CMP? This is multi. Okay, CMP. Okay, we'll see that. Two separate processor, each running its own threads. CMP is basically that the first part we read, right? That with what to say, with IoT we had, right? It's most probably about that itself. Then it concludes the topic. See, if you see multi-core and many-core GPU architecture, this is about CPU. They have spoken about CPU over here. Many RISC processors have been replaced with multi-core x86 processor, and many core GPU is in top 500 system. It's if you just read this part, you'll have more insights on what to feel about your GPU and CPU technology. Multi-threading technology. See, thread 1, thread 2, 4 issues, superscalar processor, fine grain, coarse grain. In fine grain, you say every cycle it switches after many cycles. You can see here every cycle. So this is one type, here one type, here one type, one type. Every cycle you have different type. But here you can see three cycles same, four cycles same, three cycles same, two. It's like that. Dual core, see, at the parallel left side one type is running, the second right side another type is running. Simultaneous multi-threading. Uh, Yeah, as we said over here, multiple threads execute in parallel at the same time. So many threads. So in a same line, you have more than one type of thread. So in each cycle, you have different types of threads being executed simultaneously. That's it. Then you have GPU computing to Xscale and beyond. That's what we have over here. So first key points, a GPU is a graphics coprocessor initially designed for video processing. Now it is also powered for general purpose computing, especially in high performance computing. This Nvidia CUDA is a programming model behind GPUs. So basically the first GPU also was released or come out, you can see GeForce 256 1999 by Nvidia. So mostly whenever you talk about gaming computers, this will be the first thing it will be highlighted in the websites, marketing sites. GPU outperforms CPU in parallelism, throughput, and power efficiency. What is parallelism? Running multiple tasks in parallel, okay, at the same time. Throughput, number of work done in a given time. Power efficiency, conserves or saves more power, like utilization, more power. If it is utilizing more power, then it is also performing more tasks. It's like that. Model GPUs like Fermi contain hundreds of CUDA cores and achieves teraflops performance. Exascale's computing 1018 flops demands power efficient, massively parallel systems. It's just this is a uh, very concise explanation. Just key points. In the detail, we'll be seeing over here. What is a GPU? When it was first introduced here, it is initially used for offloading graphic tasks from CPU. It is evolved, like before it was for only offloading graphic tasks from CPU. Now it is evolved for what? Video editing, game rendering, HPC, high performance computing, scientific simulation. This is for PCs and stuff. So massively parallel processor. They have evolved into massively parallel processor. Remember this as well. Then we'll go to CPU's architecture. See cores. It uses a few cores, hundreds of cores. It is optimized for low latency. As we saw in the first video, HPC and HTC. HPC, this told, focuses on raw speed, similar to that itself. Low latency in the sense what it shouldn't take much time. It should take less time. Latency is at like the amount of waiting time. If it is too much, it is very bad. High throughput, optimized for high throughput. Threads very limited and then thousands. Usage, sequential and branching logic. This is parallel data computation. Always remember GPU performs computation parallelly. See here GPU CPU is optimized for quick task switching and branch heavy logic. See here you already have usage branching logic. You can simply re-mention over here branch heavy logic. GPU is optimized for floating point operations and simple instruction multiple data style execution. We saw this in the earlier also when they said the GPU it is designed to perform SMI like SMID SIMD style itself. How GPU works? So it contains 128 plus cores and each cores have more than 8 threads, which means it has 1024 plus threads per chip. You can simply multiply 128 with 8, you can get the answer as well for that. Then you have each thread performs a small task in parallel. So we know it does performs a task in parallel way. So what do threads do? Threads is the smallest unit of process in execution, like smallest part of task in execution. So obviously it is performing something. So it's being executed. So it's every thread performs a small task in parallel, ideal for data parallel problems. Workloads are scheduled in warps group of 32 threads. See, warps are nothing but like suppose you are wrapping a gift paper, gift, right? So you just gift it. Suppose you are gifting, fruits or something. So in a basket, so you wrap it. So what are you doing? Multiple fruits, different fruits, varieties of fruits. You are just wrapping, like packing in the same thing. It's just like that. Many threads are grouped together. That's nothing but a wrap. On-chip memory and explicit memory control gives more efficiency. GPU programming model. Okay, we'll just have a look. See how GPU works is just a small paragraph. GPU programming model. We have to talk about that. See GPU. Small thing. See, I have just filtered this textbook content same to same. If you just read this para, you will see that all the points which are there in the paragraph are taken out and written over here. GPU programming model. Suppose if they talk about GPU, you can overall write about all these things. See GPU. So how GPU computing scales and beyond. We have to talk about what is GPU architecture, GPU CPU, how GPU works, what it contains. You have to say how it runs in parallel and how it is grouped. Then now we have to talk about GPU programming model. See, CPU handles logic and instructs GPU to execute floating point operations. So it's like GPU is the servant and GPU is the head. So CPU gives the task and GPU performs like that. Instructs, handles logic and instructs GPU. So whatever the brain is there, suppose I am the manager. So whatever you ask to do. I'll talk with the customer, I'll understand the needs of the customer, and I will tell the workers to do the task. It's like that. Then what instructions, what GPU executes floating point operations, all you remember, and it also designed for SIMD, simple instruction multiple data style operation, and also runs in parallel. GPU's multiprocessor contain multiple CUDA cores. Okay, we studied about CUDA is a type of core which was launched or released by Nvidia. Then GPU uses device memory and are managed using programming models like CUDA. So see what they use. You have to remember this diagram for that. So what do you have? You have multiple processor one, multiple. What is multiple processor? It processes like multiple processor being executed or processed at the same time. So see P1 to Pn is one multiprocessor. Again P1 to Pn is another multiprocessor. So you can actually extend this diagram by for drawing one more box and taking a multiple processor to like that. So what are these multiple processor doing? They are communicating with the device memory, like sharing. This is shared with device memory, and the device memory is then what shared with the main memory. The CPU handles the main memory, okay, and main memory handles the device memory, which interacts with multiprocessor, which is under GPU. GPU has what? Multiprocessors and device memory. So GPU uses device memory. See in the diagram you have that. So GPU, this GPU, okay, let me just draw it. This GPU uses this device memory for what? Managing the programming models, okay, like QRAS, or you can also say managing or maintaining, best word is managing these multiprocessors. Now what is here? CPU with main memory. See, CPU is with main memory, GPU is with multiple SMs. What is SMs? You can see here multiprocessors, okay, and then it is connected via, so this connection is what? It is a bus, memory bus for data transfer, okay. Visualizes tasks offloading from CPU to GPU. See, CPU gives a task and it is interacted, and here performance acts like that. Fifth, Nvidia Fermi GPU. So okay, we have over here exactly below this diagram we have an example of Nvidia Fermi GPU chips with 512 CUDA cores. So they talk about that 512 CUDA cores in the sense what? 16 multiprocessor into 32 cores. Okay, each multiprocessor contain integrated arithmetic logic unit, floating point unit. Since GPU perform floating point operation, so it needs floating point unit. How to remember? Arithmetic operations are performed by how? ALU. Floating point operation FLUs. I mean FPU. Floating point unit. Special function unit SFUs for transcendentals and load store units LDR STR. This is what multiprocessor contain. Then memory hierarchy, 64 KB shared per core. This is L1 is what? Core, right? It is shared per L1 per multiprocessor. So for each multiprocessor has 64 KB of core, shared core. Then 768 KB of unified L2 cache. We saw the diagram, right? So each core, suppose this circles are core, we have 4 cores, and then we have one big like this. So this is L2. Each has L1. L2 is shared for all the cores. It's like that. Then Excel DRAM. If I have to show you the diagram, which we just saw, see the same diagram. Instead of this, what is saying, they are just writing it in words. Let me just show you. See, 64 KB for each L1, 786 KB for each L2, and then 6 GB DRAM, dynamic RAM for external. It can be on chip or off chip. In performance up to 82.4 T-flops peak speed used in supercomputers like Tyne 1A, Nebulae, and Subame. Okay, towards xScale computing. So this is the next topic. As soon as you complete this, you have about power efficiency of GPU. This before this you have this. See here, power efficiency of GPU. You also have it. Towards xScale computing, Exascale 1018 flops needs power efficiency, memory and storage management, concurrency and locality, and system resilience. This was the heading right over here we saw. So if you want to improve the quality of your technology, sorry, it's see here, GPU computing excels. So about that you can talk about there over 4 things: power efficiency, how it excels using power efficiency, memory and storage optimization, concurrency and locality, system resilience. You can write your own points as well. How power efficiency is done, memory and storage optimization. You can draw this diagram. and then you have concurrency and locality, how it is, how it works, system resilience, how it manages and performs. Power efficiency of GPU. If you look at this point, you just have small place, and here itself you have, sorry, not here, over here. See, you also have all the things which are there in the paragraph. I have just 4 points. First, metrics, energy per instruction. The CPU utilizes approximately 2 NJ and GPU approximately 200. So you have to multiply this into 100, in 100 times more. G flops or what? 2000. This is year compared to 2010 year. It is less than 1 and this is 5. GPU consumes 10x less power per instruction, and GPUs are more scalable in terms of performance. Why? Simple. You're just rewriting this. See, it is more scalable in terms of GPU watts compared to CPU. GPU is more, okay. Then energy per so yeah, see it saves almost 10 times. It seems it's here we have 100 times of difference, but you can tell 10% less, 10 times less. Okay. Conclusion of that, you can just read it once. We have to read the conclusion completely. GPU have evolved from graphic accelerators to central components in HPC, high performance computer. Why that clusters are there? High HPC, what is so? Several MPPs are connected to clusters, right? So here it also does the same thing, like clusters of threads. Their massive parallelism, high throughput and energy efficiency make them essential for future computing challenges. Architectures like Fermi and programming models like CUDA are paving the way to scale systems supported by optimize hardware and software co-designs. Self-assessment, we can see. Then we have to move to 1.2.3, that is network memory management. See, memory storage and wide area networking. You have memory technology, disk and storage technology.